All right, folks, it's Bass Action back in action here. In this video, we're going to develop the formulas for our two special right triangles, our 45, 45, 90 and our 30, 60, 90. We're going to be using these triangles throughout this semester and then continuing. You will come back to them a lot in your pre-calculus classes later. So this is a pretty significant section for us. So you need two note cards for this. I gave you two of these in class. Hopefully you didn't lose those. Otherwise, go dig some out. And we're going to start with the 45, 45, 90. We're going to take one of our note cards and we're going to line it up so it's nice and square in the corner, and we can draw in this line right here. So we're going to make a square. So now we've made a nice square. You can trust that the sides are the same and the corners are nice right angles. I'm going to put my right angle markings in these two opposite corners, and then I'm going to draw in the diagonal of the square as well. That's why I didn't draw in those right angles there. Now we understand from the properties of a square that these two angles then would become 45 degrees as soon as we draw in that diagonal. Since the two legs of this triangle, or my square, whichever way you want to think about it, the legs in the triangle or the sides in the square are all the same, I can label both of these as an X. The diagonal of the square is also the hypotenuse for this right triangle that I've just created. So I'm going to label this hypotenuse. Now what I want to understand is the relationship between my legs and the hypotenuse in that 45, 45, 90 triangle. So what I'm going to do is some Pythagorean theorem. So we can set this up. I'm going to call the diagonal of the square, or the hypotenuse of this triangle, h. So I can say h squared is going to equal my x squared plus my x squared. Now I can collect my like terms on this and say h squared is 2x squared. Now what I'm trying to do is I'm specifically trying to solve for h. So I'm going to take the square root of each side, and that will give me h, and I'll have a square root of 2. And then of course the square root of x squared is just going to be x. So what we can understand is that the hypotenuse is always going to be, and we usually write this the other way around, is x times the square root of 2. Or in other words, the hypotenuse is the square root of 2 times either one of the legs. Now what I'm going to use in class most frequently is I'm going to use the extended ratio for this. So if we think about the coefficients on each of these, and we covered this in our similarity chapter, thinking about extended ratios, I can say the extended ratio for any 45, 45, 90 triangle can be expressed as a 1, 1, square root of 2, where these 1's represent the legs, and our square root of 2 is going to represent the hypotenuse. So we're going to use this pretty significantly in all of our work. So we can label this side of the note card 45, 45, 90. So this is our 45, 45, 90 triangle. Now we're going to take this note card and we're going to do our other special right triangle on the other side. So you only have one triangle that you have to keep track of. So what we're going to do is now we're going to take our note card and we're going to fold it, what you guys would often call hot dog style, so long ways. Okay, so we're going to fold that long ways and we're going to open it up so we can see the other side of it. What I want to create on this side of the note card is I want to create an equilateral triangle. So I'm going to use my second note card again. Of course, I know that length. I've divided this evenly. So I'm going to use the other end, the short end of my other note card, so I can line this up so that I've got a corner in the corner and the other edge lines up with my center line here. So I'm going to draw in that line, and then I can connect that on the other side to its corner. And you might need to pause the video while you're doing this. So now you have a nice equilateral triangle. And if you're not 100% certain, just check it. Sure enough, all three of those sides are the same. So if all those sides are the same and this is an equilateral triangle, what we know is that this angle is 60 degrees and this angle is 60 degrees. And then of course this whole angle was originally 60, but when we drew in what turns out to be our altitude, also turns out to be several other special segments, we drew in that altitude that made this angle 30 degrees and this angle 30 degrees. It bisected that angle up top. Now sometimes people do like to kind of dash in or put a little marking on this fold to kind of make it stand out a little bit for us. So similar to what we did for our square, where we had our square and we focused on just one of the triangles that was developed there, we're going to do the same thing here. We started off with an equilateral triangle, and then we're going to draw our attention and we're going to focus on just one of these triangles. Of course, it doesn't matter which one we look at. So what we're going to think about is the fact that these two pieces down here are the same. So I'm going to call this an X and this an X, because those are the same. Now if these are each x's, that means that the side of this equilateral triangle can be expressed as a 2x. So if this is a 2x, then this side of the equilateral triangle is also a 2x. So what we can already see is that in this triangle, if I'm looking at just this triangle that has a 30-degree angle, a 60-degree angle, and a 90-degree angle, the smallest side, we'll eventually call that the short leg, the smallest side, because it's across from the smallest angle, could be expressed as an x, and the hypotenuse is always going to be double the short leg, or 2x. So whatever the smallest leg is, we can double that and we'll get the hypotenuse. So what we want to understand is how can we express this third side, the longer leg? So again, we're going to do some Pythagorean theorem. I'm going to call this segment H. And the reason I'm calling this one H in this, even though it's not a hypotenuse, I'm calling it H because it's the height of the equilateral triangle. And that's going to be extremely significant for us when we start talking about area of the triangle. So let's go ahead and do our Pythagorean theorem again. So the hypotenuse in this triangle is the 2x. So I'm going to have a 2x quantity squared. And then my legs are an h and an x. So I can write that as my x squared plus my h squared. Now let's get rid of these parentheses. So 2x times 2x is going to be 4x squared equals x squared plus h squared. Remember, we're trying to get an expression for h, so we're going to try to isolate this piece. So I'm going to move that x squared over. So I'm going to get a 3x squared equals an h squared. Now I can take my square root of each side, just like I did when I was working with my other figure. So I'm going to get h equals a square root of 3 times an x. So it's a very similar expression to what we had on the other side. So I can put it down here in my picture, and h is equal to x times the square root of 3. So just like I did on the other side, I want to write this as an extended ratio. So if I write this as the extended ratio, I can write this as a 1, a 2, and a square root of 3. Now we need to keep track on this. What we know is that 1 refers to what we will call the short leg. Our 2, we can see that was on the hypotenuse. And our square root of 3 was our long leg. And again, we're going to use this extended ratio pretty significantly. So this is our 30, 60, 90 triangle. All right, and that's all we've got. And then when you come into class, we're going to be using these, so make sure to have your note card ready.